All right, let's dive into the world of magnetism. You sent us some cool excerpts from your physics textbook about moving charges and magnetism, and we're going to break it down, uncover the key principles, how magnetic fields are generated, how they exert those forces, and how this all matters to you.
It's amazing how impactful magnetism is. We can't even see it.
Right. It's crazy to think, like, way back when, electricity and magnetism, they were considered totally separate forces, until 1820, when Hans Christian Ørsted made this, like, groundbreaking observation that kind of changed everything. He saw a compass needle going all wonky near a wire with current.
Yeah, Ørsted's discovery, it was huge for science, like the first real clue that electricity and magnetism were actually super connected.
I bet that lecture hall was buzzing. Like, boom, our whole view of the universe shifts. So how did this lead to understanding how magnetic fields act on moving charges?
Well, it opened up a ton of research, leading to James Clerk Maxwell's work a few decades later. His equations basically showed that electricity and magnetism are two sides of the same coin. Electromagnetism.
Maxwell's equations. The holy grail of electromagnetism, right? What makes them so special?
They lay out the behavior of electric and magnetic fields, show how changing electric fields create magnetic fields, and the other way around. It's this like dynamic interplay. And even cooler, they predicted electromagnetic waves, like light, radio waves, even X-rays. Totally changed how we see the universe.
Mind-blowing. From a compass needle to the nature of light itself. Amazing. But let's go back to fourth. Moving charges create these fields. So how do those fields then act on other moving charges?
That's where the Lorentz force comes in. It's the force on a charged particle, moving through both electric and magnetic fields.
So it's just the sum of electric and magnetic forces on it.
Well, not exactly. Electric forces act on charges whether they're moving or not, but magnetic forces only affect charges in motion.
Gotcha. So movement is key. Say I have a charged particle zipping through a magnetic field. How do I know which way the magnetic force is pushing it?
You can use the right-hand rule. Point your thumb in the direction of the particle's velocity and your fingers in the direction of the magnetic field. Your palm will face the direction of the magnetic force.
Well, that's a neat trick. But why is the force always perpendicular? Why not just push or pull it along those directions?
That perpendicularity is really important. It means the magnetic force doesn't change the particle's speed, just its direction. So if a charged particle is moving in a uniform magnetic field, perpendicular to the field, the force will make it move in a circle.
Ah, like the magnetic field is an invisible tetherball pole.
Exactly. And that's how we can control particles in things like cyclotrons, which accelerate particles to crazy high speeds for research.
Wow, from tiny particles to the vast universe, it all comes back to this force. Okay, so we know moving charges make magnetic fields, and those fields push around other moving charges. But how do we measure the strength of the field made by a specific current?
To do that, we use the Biot-Savart Law. It lets us break down a wire with current into tiny segments and figure out the magnetic field from each little piece.
Okay, break that down a bit more for me.
So picture a tiny bit of wire with current flowing. The Biot-Savart Law says the strength of the magnetic field it makes depends on the current, the distance from that bit of wire, and the angle between the wire and where you're measuring.
So it's like a recipe, right? Changing any ingredient changes the final product, the magnetic field.
Exactly. More current, stronger field. Further away, weaker field. Change the angle, you change both the strength and direction.
It's wild how something as basic as a wire with current can create this invisible force field around it. But the Biot-Savart Law seems specific to those little wire segments. What if we have a whole loop of wire carrying current?
Great question. A circular loop of current is a fundamental building block in magnetism. If we apply the Biot-Savart Law to every tiny part of that loop and add up all their contributions, we get a fascinating result.
What happens? Does the math get super messy?
It can get a bit complex, but the result is elegant. The magnetic field created by a circular loop of current looks just like the field of a bar magnet.
Whoa, so a simple loop of wire acts like a magnet. That's awesome.
It is. And here's what's even cooler. This simple loop is considered the most fundamental unit of magnetism. Unlike electric dipoles, which are formed by separate charges, a single loop of current can create a magnetic dipole all by itself.
So we have this like fundamental magnetic unit, a loop of current acting like a mini magnet. But if we want to make stronger fields, more complex ones, what do? Just stack a bunch of these loops?
You're thinking in the right direction. We arrange multiple loops in specific ways to create stronger, more controlled magnetic fields. Two common examples are solenoids and toroids.
Okay, those sound kind of scary. What exactly are they?
A solenoid is just a long coil of wire, like a spring with tons of loops wound tight. And a toroid is basically a solenoid bent into a donut shape.
I'm picturing a slinky and a donut. Not so scary now. But why are these shapes so important for magnetism?
Their symmetry is key. Remember how Ampere's law, which connects currents and magnetic fields, works best in symmetrical situations. Solenoids and toroids are perfect for that.
Ah, so their symmetry makes the calculations easier.
Exactly. Take a solenoid, for example. When current flows through it, the magnetic field lines inside become super uniform and parallel to the axis. It's like a magnetic tunnel.
So we're focusing the magnetic field inside this tunnel.
Precisely. And the field strength in there depends on the current and the number of turns per length. More turns or more current means a stronger field.
Like a magnetic amplifier, where do we see solenoids in action?
Oh, they're everywhere. One of the most impressive is in MRI machines. Those powerful magnetic fields from solenoids are what let doctor create those detailed images of the inside of your body.
Whoa, from diagnosing injuries to maybe new medical discoveries, all thanks to coils of wire. What other uses are there?
Tons. Solenoids are also crucial in electromagnets for lifting heavy stuff and in speakers to turn electrical signals into sound waves. Plus, they're in all kinds of sensors and actuators.
It's amazing how a simple coil of wire can have such a huge impact. But you mentioned Ampere's law. Can you remind me how that fits into all this?
Ampere's law is a powerful tool for calculating magnetic fields, especially with symmetry like in solenoids and toroids. It basically says the magnetic field along a closed loop is related to the total current going through the area enclosed by that loop.
So it's not just about the current in one wire, but all the current flowing through a certain area.
Exactly. Imagine a fence around a field. Ampere's law tells us that the magnetic field along that fence is determined by the total current flowing through a whole field inside.
That's a great way to picture it. So understanding Ampere's law and the symmetry of those shapes lets us figure out the magnetic fields they make.
Right. Now, let's think about what happens when we have a few current-carrying wires interacting. Remember, each wire creates its own magnetic field. Well, when you have two parallel wires, their magnetic fields start to play with each other.
Oh, so do those fields clash and repel each other?
It actually depends on which way the current is flowing in each wire. The main idea is parallel currents attract, while currents going in opposite directions, anti-parallel currents, repel.
Wait, so if the currents are flowing the same way, the wires pull towards each other. That seems counterintuitive. Wouldn't their fields push them apart?
It does seem strange at first, but it's all about how those fields and the moving charges interact. When the currents go the same way, the fields combine to make an attractive force.
I see. Like a magnetic handshake when the currents are flowing together. What about when they're going opposite ways?
Then it's a magnetic high five gone wrong. The fields create a repulsive force, pushing them apart.
So which way the current flows determines if the wires will be attracted or repelled.
Exactly. And this attraction and repulsion between parallel currents isn't just a cool fact, it's actually how we define the ampere, the unit of electric current.
Really? Tell me more. I had no idea.
It's based on a very specific experiment with two super long parallel wires in a vacuum, separated by a certain distance. If the current makes a specific force per unit length, then we call that current 1 ampere.
That's so cool. So this interaction between two wires defines a fundamental unit of electricity. It all comes back to those basic forces we've talked about, straight wires. But what about a loop of current in a magnetic field?
That's when torque comes into play.
Torque, like a twisting force.
Exactly. When a loop of current is in a magnetic field, it feels a torque that tries to align the loop's magnetic moment. Think of it like the loop's strength as a magnet with the direction of the external field.
So it's like a compass needle trying to align with Earth's field.
Precisely. And this torque on a loop is super important. It's what makes electric motors, generators, and tons of other devices work.
Okay, I'm starting to see how these abstract ideas connect to real technology. Can you give me an example of torque on a loop in an electric motor?
Sure. Inside an electric motor, you have a coil of wire, our current loop, in a magnetic field. When current flows through the coil, it feels that torque, making it spin. And that spinning motion can power anything from a fan to an electric car.
So it's like the magnetic field is constantly twisting the loop, and that twisting is what drives the motor.
A great way to visualize it. And in a generator, it's the opposite. We use movement to rotate a coil in a field, creating a current, which we then use to make electricity.
Amazing how a loop of wire and a magnetic field can literally power our world. It all goes back to those basic principles.
It really does. And speaking of those principles, you might be wondering, how do we actually measure these invisible forces and currents?
You read my mind. We've talked about all these concepts, but how do we actually put numbers on them?
That's where the moving coil galvanometer comes in. or MCG for short. This awesome device lets us detect and measure even the tiniest currents.
Okay, I'm all ears. How does this MCG work?
Picture a delicate coil of wire hanging out in a strong magnetic field. When current flows through the coil, it feels a torque trying to make it rotate, but there's a spring fighting back against that rotation.
So it's like a little tug of war between the magnetic force and the spring.
Exactly, and the amount of rotation tells us directly how strong the current is. By calibrating the scale, we can measure the current precisely.
Like a tiny magnetic scale weighing the current.
Precisely, and that's how ammeters work. We just add a resistor in parallel with the coil so we can measure bigger currents without frying the delicate coil.
So we protect the galvanometer while still getting an accurate reading. But what about measuring voltage?
For that, we turn the galvanometer into a voltmeter by adding a high resistance in series with the coil. This makes sure only a tiny bit of current flows through the voltmeter so it doesn't mess with the circuit we're measuring.
So it's like a gentle probe, checking the voltage without disturbing anything.
Exactly. And with that, we've gone full circle from the basic ideas of moving charges and fields to the clever devices we use to harness and measure them.
It's amazing, right, how these tiny moving charges create this whole powerful force, magnetism. We've learned so much today, from those basic interactions to how they power our devices.
It really shows how beautiful physics is. When you understand those core principles, it opens up so many possibilities.
And we've only scratched the surface. There's so much more to explore about magnetism.
Absolutely. Like, we haven't even talked about Earth's magnetic field. It's like this giant shield protecting us from all that harmful radiation from the sun.
That's true. And then there's electromagnetism, this mind-blowing idea that combines electricity and magnetism into one force. We could talk for hours about that.
We definitely could. You know, thinking about all these magnetic dipoles and loops of current making these fields, it reminds me of a fascinating mystery in physics.
Oh, I bet I know what you're going to say. Magnetic monopoles.
You got it. We talked about how current loops make dipoles, but what about these elusive particles? With just a single north or south magnetic charge, could magnetic monopoles actually be out there?
That's a question that stumped physicists for ages. Imagine if we could isolate and control those monopoles. It would be revolutionary.
Totally. It would change our understanding of magnetism completely and could lead to incredible new technology.
It's like a scientific treasure hunt, searching for these magnetic monopoles. And even if we never find them, the search itself helps us learn so much and think in new ways about the universe.
Exactly. That's what's so cool about science. It's a journey of discovery that never ends. There's always something new to learn, new puzzles to solve.
Well, I think we've uncovered some awesome knowledge about magnetism today. Our listener is ready to keep exploring this fascinating field.
I agree. Keep those questions coming and never stop exploring. Who knows what amazing discoveries are waiting out there.
Thanks for joining us on this deep dive into magnetism. We'll catch you next time on The Deep Dive, where we'll be tackling another awesome topic.